Today, what we'll look at is one, I wanted to look at written homework 4 a little bit just to help people get started on that. Someone asked me about it on Monday, and the first part A, wasn't too bad, but then part B was, pretty challenging. I couldn't figure it out in the moment. And then later I sat down and looked at it, and it wasn't too crazy. I got through it, but I can see that it would definitely throw some people off. So I thought we'd go over that, particularly looking at just part A to make sure that makes sense, and then part B, at least to get the idea to help you out with it. I didn't intend for it to be quite so challenging. I guess I forgot it was that hard. So we'll take a look at that, but otherwise, we'll also look at first order topics, higher order topics, just general review. Really, it's whatever you want to look at. This day is slated as sort of the first order day, and then tomorrow would be, in theory, the higher order topics day. But really, we'll look at whatever you want, since we're here and can ask questions dynamically. So why don't we start with a few announcements. So the first announcement is just talking about exam 2 in general. I want to remind you that it is cumulative. And actually, now I'm paranoid. You guys can hear me, right? Okay, cool. So exam 2 will be cumulative. Now, as I mentioned in an announcement, it's not meant to be punitive, like to make it harder. It's actually supposed to, one, make it a little easier because now you can draw on knowledge that you've already created. And two, it also is meant just to reinforce that knowledge. Now, it's not longer. It's not like it's just, 2 exams pasted together. It's still 8 questions. Exam 1 was 8 questions, and it's similar in the sense that some questions may go a little faster, other questions may have multiple parts and take a little longer, but I intend it to be about the same in terms of length and difficulty and so on. Now, with that said, someone asked, and I thought, okay, that seems reasonable to maybe give a little bit of extra time. It's true. I want you guys to do well. I'm rooting for you too, and I want you to get the material and just do well overall. So if having a little bit more time will enable that, then that's great. Now, I should put on here, in addition to extending the amount of time you can take in the exam by 20 minutes, I also opened it up earlier and have it close later. So the earliest is going to be 7:30 a.m. if you happen to want to take it earlier than 7:50 or 8 a.m. And then it will close at 11:55 a.m. So you can start earlier or start it at the same time as you did last time, but that's the opening and closing time. And then you'll have in there, I guess it was 80 minutes before, so now 100 minutes. Now, there are going to be review videos on the YouTube page in the, elementary differential equations playlist. Namely, there is the review video from last time. That's on the first order topics. And then there's going to be a new review video. Well, it's actually been up for a while, but there'll also then be that video on higher order topics. So those 2 videos are available for you to watch. And of course, you can also ask me questions. Now, with that said, just like last time, there's now going to be 2 reviews, one being another review of the first order topics, and then one being a review of the higher order topics. In theory, today would be the first order topics, tomorrow would be the higher order, but whichever. In fact, I've had them open for a few days now, so you can certainly try both now if you want to get into them. I saw that a few people have done so. So you can go ahead, tackle those whenever you want. And then I should note that they are actually, the first order topics one is due today, even though it's been open for a while. The higher order topics is due tomorrow. So definitely do the first order first, but you can certainly start on the higher order topics if you have the time and inclination. Now, with that all said, I want you guys to do well. So I'm going to try to make myself as available as possible today and tomorrow, so that if you have questions, we can jump on Zoom and talk about it, or I can just reply with a quick email if it warrants that. I won't be able to do it the whole time I have other time commitments, but I'll try to be available as much as I can. Now, going back to what we're going to do here. First, I thought we'd open up to general questions you guys have. With that said, I want to look at written homework 4, in particular question 2. And then after that, it's sort of review of first order, higher order topics. And really, the questions here can tie into all this. So if you have questions about this stuff, don't hesitate to ask. We may jump around a bit. With that, questions that you guys have off the top of your head that you want to ask. So someone asked, can you go over how to determine singular solutions? Okay, yeah, that's a good one. So let's remind ourselves, what is a singular solution? Also, if I'm talking and you guys all of a sudden can't hear me very well, it's much quieter than usual. Let me know. I'm just experimenting with different mic positions. I changed the mic stand. So just let me know if it all of a sudden is quiet or has some other audio issue. So a singular solution. A singular solution is something of the form, let's say, y sub s, s just to denote that it's singular, is equal to some k, where k is a real number. So that means it's just some constant. It's a constant function. Now, let's say you have the following diffeq. Say you have y double prime plus 3y prime plus 2y is equal to, how about, try a variety of things. How about 7? If we want to know what the singular solutions of this are, what we can do is just substitute this y is equal to k. So maybe I'll color this. Now, if you take just y is equal to k, okay, it's just some constant. Then you want to find y prime. That's going to be 0 because you're taking derivative of a constant. Y double prime is also equal to 0. Now substitute these things into the differential equation. That is, this goes here, this goes here, and this goes here. If you do all the substitutions, what you'll end up with is 0 plus 3 times 0 plus 2 times k, and that's equal to 7. Just a little bit of algebra means that k is going to be equal to 7 halves. So there's one singular solution. When we substitute in this constant or singular solution into the differential equation here, we get that k is 7 halves, and that's it. Now, if you had a different differential equation, let's say I want to take this singular solution. Actually, let's do questions as well. If you have a different differential equation, let's say y double prime plus 3y y prime plus 2y is equal to e to the t, let's say. Now, if you do the same substitutions, you'll end up with 2k is equal to e to the t. Now, it's true that for some t, you could maybe get in a true equation here, depending on what k is, but it won't always be true. In particular, if you solve for k, notice what you get is not a single value of k. So you get k is equal to e over, or 1/2 e to the t. So k cannot be a constant in this case, which is a problem because singular solutions are constants. So k here we get is some function of t that changes, not constant. Therefore, there is no k. If k can only be a function of the independent variable that changes, then there's no such constant it can be. So in this case, there are no singular solutions. Now, this is a case where I have constant coefficients. And if you do have, I think someone asked, like in general, can we kind of guess how many singular solutions there are going to be depending on what the differential equation looks like? Yeah, to a degree. If you have, let's say, a constant coefficient differential equation, like let's say what, a0 or a2, let's say, y double prime plus a1 y prime plus 2y is equal to some function of t, and you, I don't know why I changed it to 2 specifically, but say a0. If you substitute in k into a linear constant coefficient differential equation, always what's going to happen is you're going to end up with k times a naught, and that's equal to, let's say, some f of t. And now it depends. Is a naught non-zero? Is f of t a constant? Does it have a presence of t in it, like a cosine of t or e to the t or whatever? But yeah, in this case, it's always going to amount to something like that. But you could have other cases. You could have, actually, I want to remind myself really quick. This is one I want to show you. Let's say you could have something like, I don't know, cosine of x, y double prime. Actually, that'll amount to be a similar thing. Yeah, forget, I can't think of a good example offhand, but there could be cases where, you know, you don't have constant coefficients, but if you think about taking the derivative, anything that has a derivative, second derivative, etc., the derivative of a constant is 0. So all you're going to have is the term that is just y, whatever its coefficient function is here. Oh, I know what I was thinking. Let's say you had cosine of x, y, and then you had 3y double prime is equal to cosine of x. Okay, so here we have cosine x, but if you substitute in k, what you'll get is that k is equal to cosine of x over cosine of x. And of course, for particular x, as long as x isn't a particular thing, you'll get 1. So you could say that maybe k is equal to 1, and that would solve this as a singular solution. However, what I wanted to comment on up in the right-hand corner is that if you have, let's say, a differential equation like y double prime plus 5y prime is equal to 0, and you substitute in k, what you'll get, so let y of s be equal to k, substitute that in, and you get 0 plus 5 times 0 is equal to 0. And that's true no matter what k is. Well, as long as, you know, k is a constant. So in that case, we'd actually have infinitely many singular solutions. So you could have that there's a single singular solution. You could have infinitely many, or as we saw previously, you could have none. A good question to ask would be, could you have like exactly 2, exactly 3? Could you have something besides just 1 infinitely or 0? And the answer is yes. But I'd have to think about that. Okay, so hopefully that provides a little context on what's going on with singular solutions. Then someone asked, can we go over online homework for Monday? Let me bring that up. Yeah, let me get the homework up here and then we can look at that. Okay. So the homework from Monday, day 16, that one is essentially using a characteristic polynomial to find out what the roots of that polynomial should be and then what the solution function should look like. So if we have, say, for instance, y double prime plus negative 1 y prime plus negative 12y, and that's equal to e to the 9t, the characteristic polynomial is going to be r squared minus r minus 12. That will also, now that I'm thinking about it, if you hear any like breathing or annoying noise, also let me know so then I know I need to do something different with the mic. So any annoying noise, I hate listening to that personally. So if you're hearing that from me, let me know and I'll get rid of that. So r minus 4, r plus 3. And now this tells you the roots are equal to -3 and 4. Thus, the solution formula would look like y c of t is equal to c1 e to the -3t plus c2 e to the 4t. So the a, as it's saying in that problem, someone was asking, oh, how do we find the a and b? Really, they're just looking for these roots. So this would be a, this -3 here, and this would be b. And the reason -3 is a is just because it says let a be the smaller one. So here is a, and then here is b. That's from that day 16. Hopefully that makes sense, or I explained what you were looking for. If not, just let me know. Otherwise, I'm going to jump to the next homework. On the higher order characteristic polynomials that we learned about, is finding the first root just a guess and check? Essentially, yes. In fact, I'm trying to think where that's not the case. And I can't think of a case offhand. So when you're checking a higher order polynomial, something higher than degree 2, because degree 2, you can just always use the quadratic formula. But if it's degree higher than 2, yeah, there may be a nice trick to do it in in exactly the degree 3 case, but I don't know it offhand. I don't know a lot of those polynomial solving kind of methods. And actually, it's really hard in general outside of guessing and checking. If it's not like an integer, it could be a general rational number, or well, it has to be at least one real number. But solving a cubic in general can be tough. So yeah, for polynomials of degree 3 plus, the first thing to do is just guess the first root. I should say guess and check. Yeah, that's certainly true. Next question. We post solutions for online homeworks. In particular, I think the big ones that'll be useful there, and that came up last time, was for the reviews. And what I intended to do, and I can't remember if I marked all this or not, but what I intended to do is for the reviews to stay open where you can reattempt them after the fact, / also see the answers. So maybe I'll ask you guys after you do the review, or maybe you've gone through the review already. And by that, I mean the day 18 review. So what am I saying here? I'm saying that the day 18, day 19 reviews, what I mean is for them to stay open. So I want that, or not stay open, but to be accessible. Of course, it would be it would not be graded. Like you couldn't reattempt it to improve a grade, but you could reattempt it just to, 1, have some more practice, and 2, also then hopefully also see the answers. Now, I'll double check the settings after we're done here, but that's what I mean. So if you happen to have completed it and you find that that's true, great. If you, like after today, you attempt it, or you look back at the day 18 one, see if you can still access it, attempt it, see if you can show the answers. Remember, the show answers are going to be kind of at the bottom. So you got your problem, it's asking whatever, here, put in this blank, and then the show answers should be down here, if the setting is tuned right. So double check on that for me when you get a chance tomorrow. Now let's see. The next one is, so that will be effectively posting the solutions as long as the show button is open. Someone asked, can you go over this problem? And I got to download the problem. Okay. So someone is asking a classifying question. Basically, what are all the things that this could be? So let's definitely look at it. suppose you have ds over dt. So s is your dependent variable. And that's equal to 19s. We'd then like to know, what is it? And there's a whole list of different things. So let's go through it together and just see what we come up with. So this is a little bit review, a little bit answering that specific question. Okay, so first things first. You can just type in chat just to give yourself the practice. Do you guys think this is separable? So that's the first question. And whether you're right or wrong at this moment doesn't really matter. It's low stakes, only I'm going to see it and I'm not judging. It's the time to be wrong is now, not when it's exam time. So if you're wrong, that's fine. We can correct it. Okay, I see a good chunk of people typing in chat, so appreciate it. So in fact, it is separable. The reason it is separable is because we can write this alternatively as, let's say, 1 times 19s. And 19s is a function of s, and we can think of 1 as some function of t, if you will. So in that case, yes, it is separable. While we're at it, let's also ask, is it autonomous? What do you guys think? So autonomous. And I'll just remind you, in case I'm not seeing a lot pop up in chat, so I'm guessing maybe that's a little less familiar. So autonomous is if it only depends, or the only thing that you see is the dependent variable once you write it in prime form. So if we were to write it in prime, we would have s prime is equal to 19s. So in that case, indeed, it is autonomous because it only has the presence of the dependent variable. So is it autonomous? Yes, it is. That's again, when you can write it so that it only has the dependent variable present. Once you've put it in prime notation, then it's autonomous. Okay, next thing. Let's say, ask, is it linear? What do you guys think? Again, if you think you have an answer, if you want to let me know in chat so I know whether you get it or not. So is it linear? Okay, so it is in fact linear. The reason being is you could rewrite this as s prime minus 19s or plus negative 19s is equal to 0. That's a first order linear differential equation. So yes, it's linear. Is it linear homogeneous? And actually, I'm just going to fly through the next bunch of these. Is it linear homogeneous? Yes, it is, because you have this 0 here. So it is linear homogeneous. Also, yes. That's because you've got that it's linear for 1. That's something you need, and it's equal to 0. The next thing, so we've covered autonomous, etc. So since it's linear, it's not nonlinear. So nonlinear anything, it's automatically not going to be that because you're linear or nonlinear. So nonlinear, whatever, that's going to be no, because you've got that it is linear. Let's see, we look at the order and it's first order. The highest derivative is 1. And let's see, what next? The question is, it Bernoulli? So there's really 2 more, I think, Bernoulli and exact, that we want to ask. So first, is it Bernoulli? What do you guys think? So Bernoulli is the current question. If it were Bernoulli, what we'd be able to do is write it like this: s prime plus, let's say, negative 19s is equal to this is what it would look like using some of these values. Negative 19s plus, I guess, some function of t times s to the n, where n is not equal to 0 or 1. Because if it was equal to 0, you would just have this. If it was equal to 1, you could just subtract it over, and it'd be linear homogeneous. So in fact, it's not Bernoulli, because there isn't s to the n where n is something besides 0 and 1. So no, it's not Bernoulli. All right, then the last thing is it exact? And if you remember, something I mentioned before, but maybe I've mentioned a few times, but there's an easy way to see in some cases whether a diffie-q is exact. So now the question is it exact? Yeah, and I see someone pointed out exactly what I was going to reference. Good. Yeah, so someone pointed out, nice job to the person pointing it out, is if it's separable, then that implies that it's exact. So if it's not separable, then you have to check, but it is in fact exact then. So that's a nice thing that you kind of comes along for free. Okay, good. That was that question. Now I'm going to jump back and go over a problem people asked about. Okay. Someone then asked about 4.1 from written homework 4. Excuse me. Thank you. Sorry. I hoped you guys didn't hear that sneeze. All right. Let's then look at, how about written homework question 1? We'll take a quick look at that, and then I certainly want to get into written homework for question 2, just to give you guys a leg up, but I don't want to spend too much time on it because I want to open it up for other questions for review that you have, since this will be our last time formally meeting all of us before the exam. So let me bring up written homework 4 quick, because someone asked about question 1. Yeah, so written homework 4, question 1. What that's saying is, if you have a first order diffie-qs, and this ties into the existence uniqueness theorem, then looking through a particular point, let's say a green point here, if you have, let's say, one solution passing through this point, it does whatever it does, and then it passes through here. What written homework 4, number 1 asks about, or 4.1, I should say, it says that you find the solution curves never cross. And what I'm saying, or trying to imply here, is that if you have, let's say, a dy dx is equal to some function of xy, here's x, here's y, and you look at one solution curve, red going through here, and then another solution curve, let's say blue, and it does something like this, I claim that this is not possible. And well, besides me claiming it, that's what the problem claims. And the question is why? Well, it gives an explanation in the problem, and the explanation is plug in the point that is xy here. You know, you've got the green point, it's xy. Substitute that in, and what'll happen is you're going to take the function, whatever it is, of xy, and it's going to give you some particular slope. Now, that slope is going to be based on that point. And any solution curve going through that point must have that slope. So let's say the slope is like this. Let's say the slope is at that point like so. Or I've drawn it a little bit off just to make it, oh, well, that'll work. Something like that. So if the slope is like so, and supposing it lines up with the blue, there's only one of them that you can get. So that means the blue curve would fit this slope, but the red curve would not. Therefore, any two solutions, if they cross, they're going to have differing slopes. That's going to be a problem. So that's the first part of 4.1, is essentially saying you can't have solution curves cross in the first order case because there is something like this. And let me stress, this is the first order case. The second order case is different, and hence there's a different existence uniqueness theorem. Now, I should point out, when we talk about existence uniqueness, first you want to know, is there a solution to a diffie-q? Then you want to know, is it the only one that passes through a point, or, given a set of data? And in the first order case, we have it under the conditions of Picard's theorem, or the first order existence uniqueness. But here it kind of gives you the intuition that if you have this function like so, or over here rather, the f of xy, it's going to give you a single slope, and therefore two solutions that cross through here, well, there can't actually be two solutions because only one will fit the slope, unless they happen to be the same curve, or have some other kind of weird things happening. So that's a little bit of the intuition behind the first order existence uniqueness. Now, the other part of written homework for number 1 says, in the second order case, well, what happens? Okay. In the second order case, what are you going to consider? You're going to consider, let's say, just as an example, y double prime plus, how about p of x, y prime plus q of x, y is equal to some function, I don't know, f of x. Then if you're considering an initial value problem, you have initial value data. So you have a y of 0, or actually it could be y of whatever. Let's say y of a is equal to b1, let's say b0. Y prime of a is equal to, actually let's call it b and c. Now what this means is, you have a point, color it green, maybe a point AB. That point I'll put, let's say here, that has coordinates A and B, and this is in the XY plane. You're going through this point, so that's one criteria. But then the slope there is going to be such that it's this slope. So the slope of the solution at Y, or at A, is equal to C. That would be like the following curve, put that magenta. So you have a curve and it looks like, or have a slope rather, and it looks like this perhaps. Now a solution curve going through here, let's see if we can have more than one. So you could have a solution curve that maybe looks like this. Then you might have a solution curve, a different one. Let's put these in different colors so we can reference them easily. Say we have a blue curve, and then we'll put a yellow curve. Say another curve kind of looks like this and has this property. So this is getting at the latter part of 4.1 in written homework 4. So the question is, well, is this okay? And I claim, actually, let me make it even more kind of dramatic. No, actually, that's the one I wanted. Okay, yeah, I like that. Okay, so now we satisfy this initial value data. Now the question is, you can have these intersect. Why is that true? Well, if you look at this point and you have, different y's, here's a y, and then here is one, two different solution curves. We're claiming that this is okay. They can now intersect like this. They both have the same slope there. They both pass the same point. But when you, let's say, substitute in a into the different function values, you're going to get different values here and here. And then in particular, what you're going to get out in the end, once you substitute all that in, is you can potentially get a different y double prime. And that's the, forgetting the name, not convection, concavity. So the concavity can be different. Maybe I'll put that in purple or something. So the second derivative has to do with concavity. So that concavity, notice, is different in these two cases. One case, it's up like this, concave up. Another case, it's concave down. Or it could even be, both concave up, but different degrees of concave up. So I won't say too much more about it, but that's really the idea, is you have this extra dimension of concavity that allows you to now intersect here, and you don't, because you can have different second derivatives. That's what allows you to do that. Okay, with that, I want to now look at the second part of written homework 4. Actually, I'll open up to you guys. You can decide. Do you want to look at written homework 4, the second part, or do you want to ask some questions about whatever, first order, second order topics? I'll let you decide. So in chat, what would you like to do? Go over written homework 4 too, or would you like to ask in particular about certain first order, second order, higher order topics? Okay, the first two responses I see are both written homework 4, second part. So let's certainly go over that. Written homework 4, all right. So I'm going to flip through the pages so you can see the work I've done for it. Yeah, so that's a lot of pages. I'm going to fly through this a little bit, but know that I'm recording. And so you'll be able to go over and watch this later. Specifically, maybe it's something you want to save for after the exam, so you can study before that, or you want to crack at it while it's fresh, but either way. So written homework 4, part 2, says you've got an unforced overdamped system. All right, it's unforced, so we have a second degree, and this is missing a K. We have a second degree spring mass, second degree constant coefficient differential equation that's homogeneous linear. And now what we're asked to do is figure out what should be x of 0 and x prime of 0. We're supposed to figure that out, come up with that such that two different things occur. For part A, we're supposed to find it so that what you get is a curve like this that approaches the, in this case, t-axis, but it never crosses it. So maybe it starts above and it approaches but never crosses. Then for the second part, what we do is we want it to cross exactly one time, turn back around, which gives you a 0 slope, and then approach towards the t-axis again. So these are the two parts. Now, we're not told exactly what the two roots are, except we know that it's an overdamped system. If it's overdamped, that means there's two roots. They cannot be positive. The reason being is that when you look at, let's see, how do I want to say it? Yeah, essentially, with the way K, C, and M are, I'll just sort of say this without going to the justification. But if you look at what they can possibly give you for roots, if they're going to be two real roots, they're going to be two negative roots, just because they're all positive. And if their relationship is such that you get two real roots, the discriminant is appropriate, then you get two negative roots. Now, a really important thing to do is to set it up so that you choose a particular one to be less than the other. If they're distinct and they are both negative, we may as well pick one of them to be less than the other. So let's let alpha be less than beta. So this is really critical. We're choosing alpha to be less than beta. And if it were the other way, you could just rename them. So the renaming is such that this is fine. Now, in the first case, what we'll do is we'll say that we have alpha and beta. They're real, they're distinct. We're saying alpha is less than beta. But either way, it's going to give us a solution form like this. Then you take the derivative, which is not too hard to compute in the case of exponentials. Then substitute in the initial value data, which we have to determine. But since we're trying to find x of 0, we can at least find that we have from the first equation c1 plus c2, because we have e to the 0, e to the 0. Both times that's 1. So we get c1 plus c2 is equal to x naught. Now, x naught is what we have to decide on. We have to pick it. But we at least know that c1, c2, if we add them up, we get x naught. Now, essentially what we're trying to do is solve for c1, c2 in terms of x naught, alpha, beta, etc. So we're just doing solving for c1, c2. By a similar measure, since we know the derivative of x, we substitute in 0 for t, and then that gives us this equation that alpha c1 plus beta c2 is equal to v naught. Now, here's some scratch work on the side that I'm not going to go over because it is just a bunch of algebra, and it's not the conceptually challenging part. Here, just like we've done in every other case, solving for these coefficients, you're going to, use substitution or elimination, and then you're going to eventually come to C1, C2 look like this. So here is C2, which I got just by some algebra, and then here is C1, which I also got just by some algebra. All right, that's good. Now that means we can substitute C1, C2, and now we're going to get something that looks a little messier, but is more useful to us. We're going to get this thing right here. We're going to get x of t is equal to this new C1, this expression, times e to the alpha t, plus what was C written as C2, but is now written in terms of alpha, beta, x naught, v naught, times e to the beta t. Now I'm going to remind us what we're trying to do here. I'm going to flip back. What we're trying to do here is look at this case, or pick x naught and v naught so that we get this case. Like we're in control of what x naught, v naught are. We can pick it to be whatever, but we need to pick it so that we end up with this. Now notice this is never 0. We're going to start out some positive number, and then we're just going to let it approach the t-axis. If we do that, or if we want to do that, how do we guarantee that x of t is never 0? That is, how do we guarantee that the solution will never cross? It'll always stay above, let's say. Well, in order to do that, we just have to make a guess at v naught, x naught. V naught, we intuitively have in our mind that it's some positive number, whatever. Or, x naught is some positive number because we're above the t-axis. But then v naught we can control. So you just have to guess at some things, see how it goes. If you can ever guess something to be 0, that's a good place to start because it simplifies things as far as the computation. So we'll let v naught be 0. That means let v naught be 0 here, let v naught be 0 here. If you do that, v naught 0, v naught 0, because we're just trying it out, try v naught equal to 0, v naught 0, v naught 0. Then what we get is these new expressions where v naught is 0. Now we have to do a little more supposition. All right, supposing v naught is 0, we know that x of t will look like this. All right, well, that seems fine. But now what we have to do is show that it can't be that x of t is 0. We want it to never be 0. Then we know we have this case if x of 0 is positive. All right, so let's suppose, and I should put under here, suppose for contradiction. So we're doing a little bit of a mathematical proof here, just without total formalism. So suppose for contradiction that x of t is equal to 0. That is, we're going to suppose it's 0 at some point, and after t is greater than 0. And we're going to show that actually that's a problem. So what we do is we say, suppose it is, there's some t value out here, t naught maybe, such that actually this is 0. And we're going to show, well, that can't really happen. We reach a contradiction if that were the case. All right, so supposing that it's greater than 0, t is greater than 0, we substitute it in. What we get is the following here. Then if we do a little bit of algebra, we'll get the following here. And then we get this. Now the claim is this is a contradiction. Why is this a contradiction? Well, there's one reason, but let's jump to the next page and look at why. So the claim is that we reached a contradiction in the other case. What we ended up with was this thing here. And I claim this is what leads to the contradiction. Here's why. If you look at the orange function, you have e to the beta minus alpha. The way we chose alpha and beta, it needs to be bigger than 0, or it will be bigger than 0, because we chose alpha to be less than beta. They're both negative, but whatever. Alpha is less than beta, so that means beta minus alpha is greater than 0. If you graph a curve that is e to the beta minus alpha, or e to something positive times t, it looks like this. So this orange curve would be, for example, let's see, x is equal to e to the beta minus alpha t. That's this orange curve. At the same time, you've got beta divided by alpha. Now these are both negative. So negative divided by negative is positive overall. And in particular, we said alpha is more negative. That means not only will this be a positive number, but alpha is larger in magnitude than beta. So this is a constant. This would be like x is equal to beta divided by alpha, just a constant function. And I should label these axes as t and x. Now you have two functions. One is this exponential, the other is constant. Okay, well, what's the problem? Well, we're saying that this constant function equals this exponential function for some t naught, and t naught is positive. But the exponential, after it passes through 1, it's always going to be bigger than 1 for t greater than 0. So after it passes through 1 here, it's always going to be larger than 1. And in particular, this value is less than 1. So they'll never again intersect once t is strictly larger than 0. Therefore, we have a contradiction. We have that this thing that has to be bigger than 1 is equal to this thing that has to be less than 1, less than 1. And that cannot happen for t that's positive. Now, as I say that, I realize that this all might be too fast and make no sense. Is this making sense to anyone, what I'm saying here? I stare at the chat, sweating. Okay, so let me reiterate this part. I'll mention the next part just so you have it for the video. You can go back. But what were we doing here? We were trying to find x naught and v naught such that we get this case. There's two different cases we're trying to get. We're looking at the first case A. In particular, we note that in the first case A, you never have a 0 t, or I'm sorry, you never have a 0 x. That is, this solution never crosses the t-axis. We needed a whole bunch of things to be able to argue that. In particular, we had to note, which is true, but we had to make careful note of it, that we have negative roots. We choose them so that alpha is less than beta, because you can do that. It's just renaming them if it were the other way. Then we're going to say, all right, we do all this algebra and work here, go through all this so that what we get is this formula. Then we work with this formula and do the following. The first pick that we make of V naught or X naught is going to actually be this thing here. So we decide to try out. Now, maybe this didn't work. Maybe it wouldn't have been helpful and we couldn't have reached a contradiction, which I claim was what we wanted and is good. But we try something out. We have to pick something for our X naught and V naught. If you can try 0, that's a good thing to try. It seemed like it might be reasonable in this case. So we tried it. If V naught is 0, what you get is that the position formula here, the X of t is blah, blah, blah. You get that that's here. Okay, now here's the part that I think is probably most confusing, if anything. When you, and this is really a mathematical proof, when you suppose something for contradiction, you say, all right, suppose this is true. You go through steps logically, and if in the end you reach a contradiction, you go back and you say, oh, the thing I supposed, actually that can never happen. Because if it were to happen, we would reach a contradiction. And mathematically that's not allowed. So in that case, how do you get to that contradiction? Since we said that V naught is 0, you get this here. You do a little bit of algebra and you end up with this thing. So this is the key part to end up with. This right here. Now on the next page, I expand on that and say, here's how the contradiction works. We have this beta over alpha is equal to this thing for some t that's greater than 0, and we know that alpha is less than beta. If you graph the function e to the beta minus alpha t, you get this curve. Notice beta minus alpha is positive. That's why it's going up like this and not instead down like that. That would be if beta minus alpha were negative. So it's going up positively here. And then that means after we hit t is equal to 0 for positive t values, this is never going to be anything but larger than 1. It's strictly larger than 1. Then we have this function. We have beta divided by alpha, which is going to be less than 1, but positive. These are both negative. Alpha is larger in magnitude than beta, so we get something less than 1. That means you have this, or you can graph this constant line. Then you can see, I hope visually, that these can't be equal for any positive t value because 1 is always going to be larger than 1, 1 is always going to be less than 1. So that means if V naught is equal to 0 and X naught is equal to something positive, we'll get the situation where there's a contradiction that never can we have X of t equal to 0. We went through we supposed this for contradiction, we reached a contradiction. That means that X of t is never equal to 0. So the conclusion here, once we reach the contradiction, is that, where do I want to put it? So from all this, we can say by contradiction, X of t is never equal to 0. And that's good. That means we just pick some positive X naught value. Let's have it be 1. And then we let V naught be 0 as we had. And that will lead to the conditions of part A. Now, there's another part B. And in some sense, I think this part was easier if you can make this one conceptual leap. So let's look at this quick. So what about part B? Well, this is a case where you have exactly once for a positive t, for any positive t, that the derivative is equal to 0. So what we want to do is think about what are a reasonable X naught V naught to give us this. These formulas are exactly the same from before, where I guess I took the derivative here, but it's based off of the formula we just looked at. And we can do it one of two ways. We can either find where this is 0 exactly once, because that's where it passes here. Or we can find out where the slope is 0 exactly once. And I can't remember. I just did this last night. Which one did I pick? Oh, I guess I looked at the slope exactly once. Okay. So here we'll use the slope exactly once. And I may not finish this just because I want to open up to other questions, but I'll at least show you the idea here. So setting the slope equal to 0 and then trying to find out a t and wanting it to be just a single t, a unique t, that would mean that this is equal to 0 exactly one time. That corresponds to this turnaround that we have here. The solution goes down, and then eventually it turns around, it's going positive, and then it's going to asymptotically approach. That's what we want. So we have to figure out what x naught, v naught are so it does this. That means it's equivalent to saying we would have x prime of t is equal to 0 just exactly one time here. Like last time, just try out a v naught. One might guess going back here that maybe you have a negative v naught. So, all right, let's try -1, kind of the simplest negative number we can think of. If you do that, try v naught is equal to -1. Then when you substitute it into the slope formula, what you get is this thing right here. Actually, maybe I want to move this down and then move this here. Actually, no, that was fine. So if you substitute in v naught is equal to -1, you'll get this formula. Just do the substitution. And then you can start rearranging things. So you can just take and do a little bit of algebra. That will get you to this point. Do a little more algebra, and you get to this point. Okay, now here's maybe the hardest conceptual part of all of this problem. And hopefully I explained it enough to at least give you a shot at grappling with this. Like before, we're going to graph this curve. We know that this curve is going to be a increasing function. It's going to pass through 1 when t is 0. So it looks like this in yellow here. So this here is this yellow curve. Just to be really crystal about it, this is x equal to e to the beta minus alpha t. That's this curve here. Now, in the same way as before, remember we had the green function before where it was a constant function and it was less than 1. What we want here is for this number, which is indeed orange, we want this number, these are all constants, so you add them all up, divide them, you get a constant. We want this constant function to be bigger than 1. If it is, we can graph this as just a constant function, and it will at some point intersect this curve. We want that because we want there to be exactly one t value such that this is equal to 0. So we're not going to do contradiction here. We're just going to try to find a single place where we have this intersection. That means that this is true. That means that this is true. That means that this is true. There's exactly once for positive t such that we get this intersection. What do we have? We've got that alpha is less than beta less than 0. You add x naught beta alpha to both parts of that inequality. Actually, this part we don't really need. Now, here's the big thing. So here's the maybe the hardest part. If we have this inequality, alpha less than beta less than 0, we don't even need the less than 0 part for a second here. But in this inequality, specifically this part, we add the same thing to both sides, so it maintains the inequality. Now we're going to divide both sides by this. Dividing x naught beta alpha plus beta by itself gives you 1. Anything divided by itself, as long as it's not 0, is 1. Then we get this expression here. Okay, well, what is that thing? That thing is orange. That's this constant function here. Now, what we want is for this sign here to now be opening up to the left. The reason we want that is because we want this thing to be larger than 1. In order for that to be true, what we need is, what do we want to be true? Maybe I've written something here that's not quite right. We want this to turn around. We want it to be opening up like this. The reason we want it to be opening up like this is because now we'll have this is bigger than 1, which would give us something like this. So let me take this part away. This is certainly all true up to here. So the sign should face to the left. The reason being is we want it to be bigger than 1, so we get this intersection here. And now I'll leave it to you for the final thing. And what I had written just previously, I think was a little off. But at any rate, we want it to be so that we have this true. And now, in order for that to be true, what we need is for this thing here to be, what do we want it to be? I want it to be, drawing a blank, negative. X naught beta alpha plus beta, we want it to be less than 0. The reason we want it to be less than 0 is so that when we divide both sides of this inequality by it, dividing by a negative switches the sign. So we want this to be less than 0. If we can pick this thing to be less than 0, then we'll get that this is greater than 1, which means these intersect, which means there's exactly once where this happens. Okay, again, this will probably require some rewatching, but it will go up and you'll have a recording of it. In the last minute or two, I want to open up to other questions you guys have about just whatever. Maybe let's not get into this homework problem, and just open any other questions you have about material really quick while we have a few minutes. And I'm not trying to dissuade you from looking at the homework. Rather, I just want to give other people a chance to ask about other topics that might be confusing them. Okay, so someone was asking about a question back in chat. And okay, well, I think that's our time anyways. So if you don't want to stick around, you don't have to, but if you have some more questions, you're welcome to stick around and I'll go over those if you had asked one from earlier and we didn't quite get to it. I see like Carlos, Mariam have questions. So we'll certainly go over those, but otherwise we will see you guys later. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.